Hey everyone, so in this episode we are going to be looking at determining the molar mass of an acid by titration. So we're going to get into a little bit of theory for this one. Don't get freaked out. Most of this will be clarified for you if you continue on into Chemistry 102 and beyond, but for all intents and purposes, I will show you a little bit of theory to help you kind of understand what's going on in a problem like this one. So in this problem, we have an analytical chemist weighs out 0.211 grams of an unknown diprotic acid into 250 milliliters. And then this is titrated with 0.14 molarity NaOH solution. And when we reach equivalence point, we've added a total of 25.5 milliliters of sodium hydroxide, which is our base. So to start off, I just want to remind us of the definition according to the Brønsted-Lowry acid-base definition of what an acid and a base is. So an acid is something that will donate a hydrogen ion, and a base is something that accepts a hydrogen ion. So for example, if we have hydrochloric acid and sodium hydroxide, the hydrochloric acid will break apart into this H+, and separate from its anion, which is chloride. And similarly, the sodium hydroxide will break apart into sodium, the cation, and hydroxide, the anion. And what happens is that the original sodium hydroxide will now accept, since this is a base, it will accept this hydrogen. The OH will accept the hydrogen ion, and so that will combine to form water, and our anion and cation will combine together and form NaCl, which we know is table salt. So that's why we say when we have an acid-base reaction that it forms water and a salt. So this example shows what happens in a monoprotic acid. Now, if we have a diprotic acid, as we do in this problem, let's take an example of a diprotic acid. An example of a diprotic acid would be H2SO4. And so we have this H2SO4 and it reacts with sodium hydroxide, our base, and it will form water and a salt consisting of the anion and the anion and the cation here. We know that sodium has a charge of +1, and if you know your polyatomic ions, this SO4 is a -2 charge. So the salt that's created in this diprotic reaction is Na2SO4. So the point of all this is, if we look, we find this equation is not balanced. We have 2 hydrogen and 1 hydrogen here. That makes 3 hydrogen in total. And we only have 2 over here. So if you balance this equation, you will be left with 2 here. All right, that makes 4, and then 2 here. And now, notice that this should be a 2. Hopefully you caught that, because sodium has a charge of +1, and if it combines with a -2 charge, we need 2 of them. Hopefully you caught that. But now we have a balanced equation. So the whole point of this that I want you to notice is that for a diprotic acid, in this equation, for every 1 mole, because you can write a 1 out here, right? We use 1 mole of this diprotic acid. For every 1 mole of this diprotic acid, we use up 2 moles of our NaOH. So this gives us a mole ratio. And our mole ratio for acid base for this reaction is going to be for every 1 mole of the acid, we use up 2 moles of the base, giving us a 1-to-2 ratio acid to base. So that's the theory behind how we solve this problem. Now, if that seems a little complicated to you, that's okay. All you need to remember, for all intents and purposes, is that when you have a diprotic acid, you have to remember to use this 1-to-2 mole ratio when solving. So let's see how that looks. So in this problem, we're given a molarity of NaOH, we're given a mass of the acid, the volume that acid is diluted in, and we're given a volume of sodium hydroxide used. And we want to find the molar mass of this unknown acid. So, since we know that for every 1 mole of acid, we use up 2 moles of NaOH, it would be useful to know how many moles of NaOH we've used to titrate. So we remember that molarity is moles per liter, and so if we have a 0.14 molarity solution of sodium hydroxide, that means we have 0.14 moles of sodium hydroxide for every 1 liter. And we know that we have 25 milliliters used. So if we convert that to liters by dividing by 1,000, we get 0.025 liters. And if we multiply this out, liters will cancel, and we'll get the amount of moles of sodium hydroxide. And that comes out to 0.00357 moles of NaOH. Now remember what we're solving for. We're solving for molar mass. So if molar mass is grams of the acid for every 1 mole, and we're already given grams, all we need to do is find out how many moles of acid were used up. And we can pretty easily do that using this mole ratio that we derived down here. So we know that for every 1 mole of acid, we use up 2 moles of base. And so we can use that down here to find out how many moles of acid we have. So for every 1 mole of this unknown acid, we use up 2 moles of our base, which is sodium hydroxide. So the moles of sodium hydroxide will cancel, and you'll be left with our moles of sodium hydroxide divided by 2, and that will be our moles of acid used. So if you plug that into your calculator, you get that we use 0.00357 0.01785 moles of acid. And we want our molar mass, which is grams per mole. So if we take that value and divide our mass by the amount of moles, we get 0.211 grams divided by 0.001785 moles of our acid. And if you plug that into the calculator, you get 118.21 grams per mole, and that is the molar mass of our acid. And so now we just need to check sig figs. If we look at the problem, we can see here that the thing with the lowest sig figs appears to be these three values here. They all have 3 sig figs. So we just need to simplify to 118 grams per mole. And that's the molar mass. That's the final answer. Molar mass of our unknown acid. And that's it for this video. Thanks for watching.